Hello, Mr. Claudia here. Today we are exploring the fundamental theorem of calculus. Wow, that sounds so important. You'd think that derivatives would be very important and central to calculus, and they are, but the fundamental theorem has to do with what we've been looking at the past few days, which is areas under the curve. It has to do with integrals. So first, let's just think about what we did yesterday in our last lesson, 3.5. That's where we found the area under a curve by using many small, thin rectangles. And we found that if we had an infinite number of rectangles, that we would find the exact area under a curve. And so that's what this limit here is. The limit as n approaches infinity. N is the number of rectangles. Now, it was a horrible, we did one example, it was horrible. It was really hard. And there's no way we're going to do that every time we want to find the area under a curve. So, can we do better? Well, consider this. What is the area under a curve under the curve y equals f of x from x equals a to b? So, let's just draw a quick sketch. We've kind of already done this a few lessons ago when we introduced the idea of the definite integral. I'm just looking for my ruler. I lost it. How am I going to do this lesson without a ruler? Okay, let's use this one. Okay, so this is A, this is B, and we want to find this area, everything underneath. So that is y equals f of x. Okay, so let's write the area function, right? Area as a function of x is equal to the integral from a to b of f of x dx. This is called the definite integral. We learned this 2 lessons ago. Area, that is, area is just, we can write it like this as a definite integral, a to b, and there's the function. Now, think about what this is saying, what the integral sign is saying. It's saying take the antiderivative of this. So I'm going to rewrite this as a at x is equal to the antiderivative at x plus c. Remember, we sort of introduced this in the first day, but if not, recall, we're just going to call the antiderivative big F. So this is the function, this is its antiderivative. Okay, but we also know the boundary condition, and this is great because we know all about boundary conditions from our second lesson in this chapter. We know that the area when x equals a is 0, because think about it. The area from a to a is just 0. The area when x equals b is a lot, but the area when x equals a, well, from a to a then is just 0. So I'm going to sub this boundary condition. I'm going to sub in a at a is equal to 0. I'm going to sub that into this expression. So I end up with 0 is equal to f at a plus c. Remember, c is that constant when we do definite integral. So c is equal to negative f at a. Now I can sub this in to my final expression. So therefore, a at x is equal to f at x minus f at a. So if we want to know what is the area at x equals b, to do that we sub in x equals b. And we end up with the area at b is equal to the area at, or the antiderivative at b minus the antiderivative at a. Right? Remember, big F is antiderivative. So this is antiderivative at b, or at x equals b would be more appropriate. X equals b and this is the antiderivative at x equals a. This is it. This is the fundamental theorem of calculus. If you want to find the area underneath the curve, you find the antiderivative, sub in b, which is your upper limit, subtract the antiderivative, and you sub in your lower limit. So it brings it all together. It allows us to now find the area under a curve algebraically. So if f is a continuous function on this interval a to b, and f is the antiderivative, then the definite integral from a to b at f of x dx, also known as the area under the curve, is equal to antiderivative of f with the bounds b and a and b, or if you want to actually write that out, that's f at b, big F at b, minus big F at a. This is all a lot of letters. Let's look at some practical examples. You'll see that's very clear how we do this. So let's say I have an integral, x cubed from -1 to 2. So we know in our heart of hearts, this is saying what's the area under this curve from -1 to 2. But we don't know how to solve it yet. Well, we do now because we have the fundamental theorem of calculus. The fundamental theorem of calculus says, hey, go ahead and find the antiderivative. So what's the antiderivative of x cubed? Well, it's x to the 4, and then we need a quarter in front. There we go. Okay, now the fundamental theorem of calculus says, well, to figure out the area, you take that, and now you're going to sub in the bounds, 2 and -1. I do this ancillary step to show that I found the antiderivative, because my next step I'm subbing in numbers, so it gets a little confusing. A quarter, 2 to the power of 4. I've subbed in the upper bounds, 2. And then I subtract 1/4 with the lower bounds. So again, what I did here is I sub x equals 2 into the antiderivative. And here I sub x is equal to -1 into the antiderivative. Now it's just mathematics we have to do. We have a quarter times 2 to the power of 4, which is 16, minus a quarter, -1 to the power of 4 is even, so it's perfect squared. So I end up with 16 over 4 minus a quarter, so I end up with 15 over 4. So there we have it. We have a quick way to find the area under this curve from -2 to 2. It's called integration, right? Or the antiderivative. You find the derivative of this, and then you sub in the bounds and subtract. Look, this integral, remember I talked about it, this is called a definite integral when it has bounds like this, and the answer is always a number. If you're curious, what happened to c? I missed writing out the c. Well, let's look at it. If I take the antiderivative of f of x, I end up with, let's say there was a c. So I have f of x plus c. So now when I do this substitution, I sub in b, so I get f at b plus c minus f at a plus c. So you can see that my c's cancel out, and I'm left with f at b minus a. So the c happened, but then it was subtracted out. So when you have a definite integral, you don't have to worry about the plus c. I think we talked about this on our first day, but we'll just revisit it again. An indefinite integral. This is the one that has a plus c. This is an algebraic expression. This is the first few section, the first section of the chapter. Definite integral has no plus c. It's a numerical answer. And it can be found with the GDC. So what's neat is the calculator is very good at finding these, but it can't find these. And we'll see that once we start using the calculator. let's tourner la page and start finding some definite, we definitely want to find some definite integrals. So this first one, first of all, and sorry it's a little tight on space here, so try to fit it all in. Okay, I need to find the integral of this. Well, the integral, or the antiderivative, it is u minus 1 to the power of 3 with the third in front. And then I have my bounds. Okay, the curly bracket tells me to sub them in, so here we go. I end up with third, 1 minus 1 to the power of 3, minus a third, negative 2 minus 1 to the power of 3. 1 minus 1, that gives me a third times 0 to the power of 3, minus a third times negative 3 to the power of 3. Okay, 0 times anything is going to disappear. This is going to become 0. So I end up with negative 1/3, and negative 3 to the power of 3 is negative 27. So I end up with negative 27 over negative 3, which gives me positive 9. That's the area under the curve, or a definite integral. Should we do another one? Why not? So, let's do this question. Now, I can't take the integral of this. It's hard because it has a quotient rule involved. I'm going to rewrite it so it's something a little easier. How about the square root of t over t minus 2 over t. I'm going to split it up. Same denominator. And then actually I can even simplify it a bit more. I end up with t to the half minus 1. So this is t to the negative half minus 2 over t dt. Okay, now let's find some definite integrals. Well, let's find the antiderivative first. So this is going to become t to the half. That means I need a 2 in front. This, don't be confused, don't be tricked. This is 2 ln absolute value t. And then we have my bounds 4 and 1. Now I just have to sub in my values. So I end up with 2 times 4 to the half minus 2 ln absolute value 4. Well, it's just 4 now, because the absolute value of 4 is just 4. So let's write that. And then we can technically, that's in brackets, I mean whatever way you want to look at it, minus, let's put a big bracket here, 2 times 1 to the half minus 2 ln 1. Aren't you glad you're so familiar with lns? Because we know this is just ln 4. You can shout it from the streets or the top of the building. What's ln 4? And it's just a number. Let's see if we can solve this. So first of all, square root of 4 is 2. So I have 2 times 2 minus 2 ln 4. And then let's keep this in brackets because there's negatives involved. So we have minus, okay, square root of 1 is 1. So we have 2 minus and 2 ln 1. What's ln 1? Go, someone shout from the top of the school. What's ln 1? I mean, really, this is saying e to the power of what gives me 1. If you don't believe me, check on your calculator, but it's always 0. So this is going to be 2 minus 2 times 0. So this gives me 4 minus 2 ln 4 minus 2. So my final answer is 2 minus 2 ln 4. That's a beautiful answer, very exact answer. You might be stressed out about saying ln 4 there, but that's just an exact number. You can type it in to your calculator if you're not sure what it is. Okay, let's do another question. Here we go. So, I have this thing in the denominator. Looks like a quotient law. Oh, let me just rewrite it so I don't have that issue. 6 to 2. Sorry, this is 2. This is 6 up here. And this becomes 2x minus 3 to the negative half dx. This is one of those tricky integrals, this tricky antiderivatives, because I have a chain rule, a function within a function. Luckily, the function on the inside is easy. It's just linear, so I know there's only going to be an extra constant. So you could use that formula I taught you, but again, I like to just do this methodically. So let's start. Something to the power of negative half is going to become something to the power of half, and I need to put a 2 in front to undo that half when it comes down. But then you have to consider the derivative of this is going to produce a 2, so I need to put an extra half in front to undo that chain rule. There it is, and I can put my bounds. Now the half and the 2 cancel out. Let's just get rid of those. So now I'm ready to sub in my values. So I have 2 times 6 minus 3 all to the half minus 2 times 2 minus 3 all to the half. Oh, yes, that's right. Now just be careful with your algebra. 2 times 6 is 12 minus, so this is 9 to the power of half minus 4. Okay, so minus, this is 4 minus 3 is 1 to the half. That is basically square root of 9, which is 3, square root of 1, which is 1. And there I get my final answer. Here you have a beautiful IB style question where you actually know what the area is, you know the definite integral solution, you don't know what the bounds is. And there's lns involved. So this looks like a nightmare, but I mean, there are only so many things you can do when you see an integral. When you see an integral like this, you can try to use the fundamental theorem that we just learned with the antiderivative, and you sub in the bounds. Let's see what that does for us. So what's the derivative, integral, antiderivative of 1 over 4 minus x? Well, it would be ln of that thing and then you have to consider, but there would be a change. This is a function within a function. What's the derivative of this? -1. So I actually need an extra negative out in front. And there are my bounds. And I know this whole thing, they've already told me, is going to be ln 3 over 2. Now, you might be saying, why didn't I use the absolute value bars here? Well, I could just say, I know that 4 minus x has to be greater than 0. So I know then that for x has to be less than 4. But that's going to be irrelevant. Like, we're actually trying to solve for m here. So let's not worry about this too much. Let's just do the math. Okay, the only thing I can possibly do now is sub in my values and see what happens. So I end up with negative ln 4 minus 2 minus negative ln 4 minus m, and that is equal to ln 3 over 2. Okay, so now this is no longer a calculus problem. All the calculus has been done. Now this is an exponents and logarithms question. Well, let me clean it up a bit. This is going to become negative ln 6. The negative is going to become plus ln 4 minus m. Oh, you can see the other limitation here, 4 minus m. We need 4 minus m has to be greater than 0, so m has to be less than 4. Okay, that's fine. Again, that's just an easy way of doing my of checking my restrictions as I go, as opposed to checking them at the end. So now, what I need to do is think back to my log training. This is an equation, has an equal sign in it. It has an m in it, one unknown. So this is an equation, a logarithmic equation. There are two methods for solving logarithmic equations. The first is to get the two logs on either side to have the same base. Then you can set the arguments equal. Ah, look, we're pretty close to that. I mean, let me write this in the other order. This looks like I could combine these using a log law. So that's a log law that allowed us to do that. And look where we are now. I have a situation where I have lns on both sides with the same base, ln e, or log e. So now I can equate the arguments. Now I can solve this problem, the ensuing problem. I can multiply both sides by 6, so I get 4 minus m is equal to 18 over 2. That gives me 4 minus m is equal to 9. Subtract 9 from m Okay, so this gives me m is equal to negative 5. Remember, m had to be less than 4, which it is. M is negative. If you want, you can even test that, right? That was the whole thing with the restriction. 4 minus 5 gives me 9, so that's a valid answer. Okay, so you can see how we could get some tricky questions. We taught you logarithms so long ago, but they come back. And this is very much within the scope of what you could see on an IB question. Let's do one more question, and this is a question, the last type of antiderivative that we learned, one that involves substitution. So, or you might be able to solve it without substitution, but essentially it's a function within a function, and then an extra function there, which happens to be a derivative. So there's like a chain rule situation here that just works out perfectly, if you remember back to lesson 3.3. So I'm going to try solving this with substitution. So I'm going to let u is equal to 1 plus x squared. If you remember the procedure, now I find the derivative of this with respect to x. Well, the derivative is 2x. Now I cross multiply and I get du is equal to 2x dx. If you want to write this out just in a nicer order, you end up with 1 plus x squared to the power of 3 times negative x dx. Now let's start doing some replacements. This thing here, we just decided that was u, but we have to get rid of this negative x dx. And here we have x dx, but we can't replace it with d, like we have to get it to be a perfect match. So what I'm going to do is divide both sides by 2. That gives me du over 2 is equal to x dx. That's pretty close, except there's a negative, so I'm going to multiply both by negative. So now I end up with negative du over 2 is equal to negative x dx. Basically, I just did some manipulation so that this thing, negative x dx, I can do a direct replacement with negative du over 2. So now I'm ready to solve. The integral from the integral is going to become, okay, so this is going to become u cubed, and this is going to become negative du over 2. Let me rewrite that as negative half, because that's a constant, integral u du. Okay, now here's the big problem. This integral has limits of integration in terms of x. This integral has limits of integration in terms of u. I can't just use these over here, because these have to do with x's, these have to do with u's. So if you're going to use this equation to solve, you have to find the new bounds, the new limits of integration. I'll do that down here. If x is equal to negative 1, well, what is the corresponding u? Well, I sub that negative 1 into my expression for u. So I have 1 plus negative 1 squared. That gives me 1 plus 1, which gives me 2. So that's my new lower bound. And, no. Okay, and similarly, if you have the other bound, which is 2, x is equal to 2, sub that in, so you get 1 plus 2 squared, which is 1 plus 4, which is 5. That's the new upper bound. So now, let's bring those up here. This is a 2, this is a 5. 2, 5. So now we just proceed with the definite integral, which is a quarter u to the power of 4, 5, and 2. So I end up with negative half quarter 5 to the 4 minus quarter 2 to the 4. End up with negative a half. Let me factor out a quarter. That'll make my life a bit easier. Now I have 5 to the 4 minus 2 to the 4. So I get negative 1 over 8 5 times 5 is 25, 125, 625 minus 2 times 4 is 16. So I end up with negative 1 over 8, 609. So my final answer is negative 609 over 8. So this question, you have to be careful that solutions involving substitution require change the limits of integration. I should say, and you can ask me to show you this, but unless you sub x, or u equals 1 plus x squared back into the antiderivative. So the one way of getting around this is you could, at this point, once you've done the antiderivative, you could now sub back in u equals 1 plus x squared, so into this, and then you could use the actual x limits of integration. So you can ask me to show you that, but if you are going to do substitution, change to u's. If you're going to use u's, then you have to make sure your bounds are in terms of u. Okay, our homework is somewhere page 310, number 1 to 10, and 312, number 1 to 10. Good luck with that, and we'll see you next time.